Hi everybody. This is the material that you will need to do your midterm lab portion of your exam. That will be next Tuesday, which is the 22nd of February during our regularly scheduled lab time. Now, at 2 o'clock on Tuesday, for both the practical surveyors and the engineering surveyors, if you wish to come in early to ask me questions about this, I will be available at that time. Or if you're very confident and you want to get started right away, you can get started at 2 o'clock. So the document I'm going to show you is going to be posted to the Moodle page and will also be available to you the day of the midterm exam. But the quality of your work on this exam is going to determine your grade. Half of your grade in the midterm will be determined by the quality of your work, and half will be determined by the quality of your field notes. So everything is in this document. I'm going to go through it kind of step by step to explain it, and I have a little stub of an example to help you get started. All right, so here on this document, the lab portion of the midterm is to determine the elevation difference between 2 points, but these 2 points have an obstacle in between them. So you've determined elevation distance between 2 points, but when you have an obstacle in between them, what you need to do is to set up a temporary point between them, find the elevation difference between the first point and the temporary point, and then find the elevation difference between the temporary point and the second point. Then to check your work, you need to come back and get the elevation difference between the second point and the first point, which of course should be exactly the same as the other way around, because neither of those two permanent points, which are called benchmarks, should have moved location or elevation. So what we're going to do then is do this using a differential level. And what we're going to do then is to assign an elevation of 100 feet to the datum, or the first benchmark, because we really don't care what the actual elevation is. Which we're caring about is the difference in elevation. So we may just assign a 100.00 elevation to our first benchmark, determine then the elevation of our second benchmark, and then come back and redetermine the elevation of our first benchmark, which of course should be 100.00 feet in a perfect world. We're also going to incorporate some of the ideas of error theory, because if your numbers are not perfect, which they probably won't be, we'll decide if they're good enough for, the job. Good enough for government work is the phrase that came to mind, but if it's good enough for the work. So right here we have definitions of some key terms, and we have set, benchmark, temporary benchmark, turning point, or sometimes that's called a temporary point. Backsites, foresights. Backsites are sometimes referred to as plus sites. Foresights are sometimes referred to as negative sites. What these refer to is when you have the instrument, the level set up, and you go backward in your loop, which of course is relative, that's your back sight. When you go forward in your loop, that's your forward sight, or your foresight. The height of the instrument is the elevation from which you're shooting, which is it's a calculated number, and the balancing of sight. Now, we've talked about the idea that the Earth is curved, and we've done some PowerPoints and some exercises about the curvature of the Earth. So since the Earth curves pretty much in the same amount in all directions, and refraction operates in the same amounts in all directions, if you balance your backside and foresight, meaning that if you keep the length of your backside and the length of your foresight approximately the same, you will not have to do a curvature or refraction correction. So this is actually our plan for the midterm. Okay, closed circuit, it's also called a loop or a closed traverse. That just means that we're going to go from benchmark 1 to benchmark 2, and then to check our work thoroughly, we're going to come back to benchmark 1. And if we have the same elevation of benchmark 1 as we did initially, we're pretty confident that our work is correct, because otherwise it would just involve some strange random error where one side of the loop had the same error in negative as the other side of the loop. So unless you're, cheating, that's not going to happen. And the closure, of course, is the difference between the beginning and the end. So getting to the theory, we've already done this in the field, which is why we're doing it as a midterm exam. We've set up the instrument, the automatic level. We've taken back sights and forward sights. We just haven't, we're incorporating this new piece of when we are taking an intermediate reading and then coming back. Okay, so what we're using as our datum, we're saying that the first benchmark is going to be at 100 feet, and I'm going to show you a note form in just a moment. And then we take these back sights and foresights and determine the height of the instrument and the height of the temporary points and the height of the second benchmark, which is really what we're getting at. Okay, the reducing errors, here are just some ideas about not building error into your loop. And the most important thing with a level, as I said, you have to level the level first. So make sure that your bubble is centered and make sure that you're centered on the entire plane. Remember, don't just shoot it on a line, but make sure that you turn the instrument and level it in the second line so that you get a good chance that you're leveled in the plane. All right, so then there's just some other things that you can check through here. Avoid the common mistakes. And go through and just make sure that you're using a good procedure. Okay, the page check is really kind of the new piece of this, and I'm going to introduce you to this idea in just a moment. But a page check with a differential level loop is almost 100% certainty of accuracy. So it's really kind of a cool part of this procedure. All right, so just like in your other labs that we've done, I ask you for the equipment that you're going to need and the proper note form, which I'm going to show you 2 examples, and you'll be able to do your own notes from here. Now, it's very important to notice, I'm telling you this, I'm recording this on Wednesday, February 21st, so you have nearly a week to make sure that this is true and that you are prepared. You must have your notebook. Your notes for this midterm exam must be recorded in your field book. There we go. And it has to be in your own handwriting, and you have to do it yourself during the procedure. So make sure, 100% sure, that you bring your field book to the midterm. Okay, so as we said, the purpose is to find the elevation difference. There's a little bit of a procedure, some of which you've already followed, but I have a picture down here, a little diagram that I'm going to go to next to show you a little bit better, and then to show you how it looks when you record it in your note forms. Okay, so this is kind of what a level loop would look like. Now this one is a little more complicated than the one we're going to do. We're going to have fewer temporary points, fewer instrument setups. But basically what's going on here is we have some sort of a benchmark here, and we have some sort of a temporary benchmark over here. So what we want to do is to establish what is the elevation difference between this benchmark and this temporary benchmark. In the case of this class, we're going to be just establishing the elevation difference between 2 benchmarks. But as you can see, the little symbol here that looks like pi, the little symbol here that looks like pi, 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 this is the same symbol that I've used in class to show you this is where the instruments are set up. So for this lab, for this loop, they would have had 1, 2, 3, 4, 5 instrument setups. I think we're going to have maybe 3 or 2, 3, or 4. It depends on how I set this up when I go outside. So anyway, if you look at this, what they've done is they've put a spike or some sort of a marker at their temporary benchmarks and temporary bench points, so which I will do for you. So I'll mark a point here, mark a point here, and then you will have to find the elevation difference between them. So the first thing you'll do is set up the instrument. And if you are able to see from benchmark 1 to benchmark 2, that's fine. You could just set up the instrument somewhere in the middle. But remember, the length of your back sight and the length of your forward sight have to be approximately the same. When I say approximately, I mean within, at short distances, maybe within 10 or 15%. But here what they've done is they set up the instrument here, and they set a temporary point right here, which means this is just, they put a spike in the ground, and they're going to shoot to it and then from it. So follow me closely here. Here's the instrument. They put the instrument here, they put the level here, they put the Philly rod here, and they backsight. They get a reading of 7.13. They leave the instrument here, but they leapfrog the Philly rod over here to temporary point 1, and they take a reading. That would be the forward sight, and so they get a reading of 4.26. Now they leave the Philly rod here at TP1. They move the instrument, leapfrog fashion, to this point where they can visualize TP1 and TBM. And then they back sight to this, forward sight to this. They continue with that. They leave the Philly rod here, put the instrument here, read to the Philly rod, leapfrog the Philly rod, leave the Philly rod, move the instrument, take a back sight, take a foresight, move the instrument, back sight to the Philly rod, and forward sight to the original benchmark. So this is the procedure. At every reading, at every time you set up the instrument, you take a back sight and a forward sight. Now the next part of this is it's very important that you record this in the proper manner in order that we can, at the end of the day, add your back sights and your foresights, add all the back sights together, all the forward sights together, and see how much error there is in your loop. So what does that look like? That looks like this. These numbers relate to the drawing that I just showed you, and it also shows you the proper note form. Differential level loop, NWC midterm exam, BM1 to BM2 in a closed loop. Now I've put the information that you'll need over here and over here. The only thing that is missing here is that you will also need to draw a picture of your loop. I've not done that because I don't know what your loop is going to look like. I suppose I could have put in a picture like this onto the note form somewhere in here, but when you do it, you will have to have a picture. All right, now the most important thing is this side of the page has to be written out in these exact columns. The first column is station. The second column is back sights, and I put a plus there to remind myself that you add. The next one is HI, which stands for height of the instrument. The next column is FS, foresight, with a minus, reminding me that I subtract those. And then I start with an assumed elevation, as I said, 100.00 feet for benchmark 1. So the information in black, BM1, TP1, is the stuff that I start with. It bears directly to the picture that I just showed you. The rest of it you'll have to fill in until your last entry right here will be benchmark 1, because you'll go benchmark 1, temporary point, maybe benchmark 2 or another temporary point, whatever, and then your last entry will be benchmark 1 again. So if you notice that we started with 100 feet, and you'll notice that from the instrument, I had a back sight to BM1. So you think about this. The column is back sight, the row is BM1. So the data that I got, 7.13, that reading goes right here. My forward sight to, which is forward sight is this column, to temporary point 1, my reading was 4.26. Now, I want you to take a look at this. I'm going to go back to the other page to show you 7.13, 4.26, height of the instrument. Height of the instrument, back sight to the benchmark, 7.13 feet, forward sight to the temporary point, 4.26 feet. So in other words, you're taking this loop, these pieces of data, and translating it into this form. You notice the height of the instrument is in the middle. So think about this in rows and columns and diagonals. So here I am set up at the height of the instrument. I back sight to BM1, forward sight to temporary point 1. Okay, with an assumed elevation of 100 feet, my height of my instrument is the elevation of the benchmark plus the back sight, 107.13 feet. And I know that my forward sight was 4.26, that's minus the elevation then of my second, or my temporary point, is 107.13 minus 4.26, which is 102.87. I continue in this fashion until I get back to benchmark 1. This symbol is summation, so that means when I'm all done, I add all my back sights. This symbol is summation, that means I add all my forward sights. Those are the only two columns that I add. And I put that number here, the sum of the back sights, sum of the forward sights, and in a perfect world, they're going to be exactly the same. So now we're going to talk about if it's not a perfect world, then what happens? Okay, that's where this is. The loop misclosure is the difference between the backward sights and the forward sights. So if it's 0.05 feet or 0.09 feet, it would be this number minus this number equals 0.09 feet. And then we have a formula for calculating the permissible loop misclosure, and we can decide if the loop is okay or not. And then we'll state the adjustment at the end. And I don't think we're really going to do this. I think we'll leave this for another time. But we're definitely going to have to do the loop misclosure and the permissible misclosure and make a conclusion whether our loop is good enough or not. Okay. And this is what you will turn into me for your grade on the midterm exam. So you notice what else we have here. The date, the weather, the party, what instrument you're using, all the stuff that you'll state, plus a picture, and then when you're done, you need to sign your name. Okay, so here is a larger picture of the note form. A little bit more about error adjustment here, but you'll see all the backsides. The backsides for this loop, not the same one as the picture. This is a different loop, more complete. The sum of the backsides is 40.24 feet. The sum of the forward sights is 40.21 feet. So the loop misclosure is this minus this, which is over here 0.03 feet. The permissible loop misclosure is whatever order we're using times the square root of the number of sights we took. 1, 2, 3, 4, 5, 6, 7. We set up the instrument 7 times on this loop, so it's times the square root of 7. If we set up the instrument 3 times, this would be the square root of 3 and so forth. Anyway, we take that times that number and we get our allowable misclosure. You can see that our actual misclosure here is 0.03 feet. The permissible misclosure is 0.05 feet. So yes, we are within tolerance and we can adjust. And like I said, we're not going to do that. It's a little bit too, it's just too much information. It's quite easy, but what we need to do is just get elevations. We'll talk about adjusting it next week or after spring break, actually. Okay, so here is the standard in the class, either 0.007 times the number of 100 feet in the closed circuit or the number of links. Now, like I said, what we will be using, this is called a third order. Ours is a little bit simpler. We're going to be using this adjustment, meaning that it is 0.02 times the number of readings or the number of times we set up the instrument. So let's take a look at this one. Okay, we'll decide what that is. And you can look at this. If you pace it off, you can say, okay, let's say my closed circuit is 900 feet. That means that the number inside of the radical would be 9. Okay, so if you take 9 and multiply it by 0.007, also check that to see what that allowable error is. And in this case, I'll let you, the allowable error will be whichever of those two numbers is greater. Okay, so you have all of the information that you need to complete your midterm exam. I'm going to post this material prior to the 22nd, Thursday. So this is the lecture for Thursday, February 22nd. I had to look at my clock to make sure I was right. So look at this material. On Tuesday at 2 p.m., whether you're in practical surveying or engineering surveying, you can come into the classroom and ask any questions that you have about this lecture. I expect you to have it watched and to have your stuff printed off and to understand what it is that's expected of you, but I'll take any questions that you have, or you can get started on your loop early. And I will put you into groups and I will assign the groups. So since we only have 2 working levels, you know, you can kind of do the math on that. You can figure out we'll have 2 groups to complete the midterm. You're definitely allowed to work with each other, but once again, each one of you has to fill out your field notebook and I will grade you on your field notebook. So that's it, gentlemen. We will see you Tuesday at 2 o'clock with any questions, no later than 3 o'clock to get started. See you then.